I got 99 problems today, and this is not one. This is problem 1524, number of subarrays with odd sum. Sum problem. Given an array of integers r, return the number of subarrays with an odd sum. Since the answer can be very large, return it modulo 10 to the 9 plus 7. Okay, so, right, we know what a subarray is, right? It's this continuous block of the initial array, and if we sum all the elements within that continuous block, that sum should be odd. So when we look at 1, 3, 5, of course, the suboptimal brute force solution would be, okay, let's just look at each of these subarrays, right? So there's the subarray 1, there's the subarray 1, 3, there's the subarray 1, 3, 5, there's subarray 3, subarray 3, 5, and the subarray 5. And if you sum together the elements of each of those subarrays, so if you sum together 1, that's an odd subarray, right? You subarray 1, 3, you get 4. That's not an odd subarray. You subarray 1, 3, 5, you get 9. That is an odd subarray. You sum 3, you get 3, which is an odd subarray. You sum 3, 5, you get 8. And that's not odd. And then you sum this subarray, just 5, you get 5, which is, so the answer are 1, 9, 3, 5. So you get output 4. Something to note in this problem, right? We don't actually need to know what the subarrays are. Meaning, like, we don't need to return the subarrays that are odd, and we don't even need to return the value of the subarrays are odd. We just need to return the number of subarrays which are odd. Okay, so that it has some, space implications, I guess. Right? We don't need to maintain all this additional information. We just need to maintain the number of subarrays that meet this odd sum condition. An array equals 2, 4, 6. So here are all the subarrays. If you sum them all together, you only get even numbers, so the answer is 0. And then here's a pretty well-involved example, and there's 16, and we could maybe work through that if we wanted to know how this is supposed to work. So this problem is interesting because maybe the intuition required relies on some basic discrete math understanding and the nature of even and odd numbers, okay? So I guess the first thing I'll say is, if you had, how will I start here? If you had any subarray, okay, so let's just create a subarray, and we'll give it a generic elements A, B, C, and D, okay? Now let's say that the sum of this subarray, A, B, C, and D, so let's say it's out of some initial subarray, right, G. Let's look at A, B, and C as a subarray, okay? If we looked at A plus B plus C, okay, what am I trying to get at? Well, let's say that A plus B plus C is odd. What would that mean? Well, for something to be odd, if you use the definition of an odd number, that means that A plus B plus C equals 2x plus 1 for some x, okay? So that's basically just saying that for some x, there's the case that A plus B plus C equals 2x plus 1 because it's odd, okay? And in another universe, if A plus B plus C is even, that means that A plus B plus C equals 2 times y for some y, okay? Now, if A plus B plus C is odd, and we want to say, okay, well, we know that this is an odd sum array. What happens if we add D to the equation? So what does that mean with respect to D? So what is A plus B plus C plus D then? Well, D can be two things, right? D by itself can be either odd or it can be even. So if D is even, that means that D equals 2x prime, right? So if we add A plus B plus C together, plus D, so A plus B plus C plus D, A plus B plus C equals 2x plus 1, because it's odd in this left kind of universe. So A plus B plus C plus D equals what? 2x plus 1 plus 2x prime. I don't know what I was doing here. And then if we do some factoring here, and just bear with me here because you're probably like, what is this guy doing? Why is he going through all this, weird discrete math-based algebra? What I'm trying to basically say is, okay, if this subarray is odd and we add in an even number, you'll notice, so we replace a plus b plus c with 2x plus 1 since that's odd, and we replace d with 2x prime since it's even. Right? When we add that together, when we factor out a 2, we get another 2x plus x prime plus 1, and you'll notice that this is the definition of odd. So this is odd. So I kind of guess the observation here is if you have an odd subarray, and add an even element, it becomes odd. Right? So basically, I guess our first observation here is you take an odd, you add an even, you get an odd. Okay? What about if D is odd? Well, if D is odd, and I'll just quickly go through this because I don't want to spend too much time. If D is odd, so we'll just erase some stuff here. What would that mean? If D was odd, it would be 2x prime plus 1. So then 2x prime plus 1. So then this would become 2x plus 2x prime plus 2, which equals 2 times x plus x prime plus 1. So this is the definition of even. So if you have an odd subarray and you add in another odd element, it becomes even. So if you have an odd and you add in an odd element, you get an even. Okay, and then what about on the other side? So we'll just quickly go through it. I won't walk through the whole thing. So if you have an even subarray and you add in an odd, well, we already have that case, right? When you have an odd and an even, you get odd. So if you have an even plus an odd, you get odd again. So we don't need to go through that. But what if you add an even and an even? So you add another even element, 2y prime, you get 2y plus y prime. So then you get an even plus an even, plus an even gives you an even. Okay, so does this give you everything? So an odd plus an even gives you odd. An odd plus an odd gives you even. And an even plus an even gives you even. And that's kind of every case that you need to consider here, right? So how do we use this idea to think about the solution? Well, I guess we should look at maybe this example using this idea, right? If you have an odd subarray and you add an even, it creates another odd subarray. If you have an odd subarray and you add an odd, it creates an even subarray. If you have an even subarray and you add an even, it creates an even subarray. So let's look at the example now that we have an understanding of this information of the array equaling 1, 2, 3, 4, 5, 6, 7. So how is this going to work? If we think about it, we think about what? What are we thinking about? If we look at 1 alone, right, let's just look just at the value 1. Well, the value 1 is going to be an odd subarray. So let's keep track of odd subarrays and even subarrays. And that's going to give you 1 odd subarray of length 1. And there's 0 even subarrays. What happens when you add a 2? When you add a 2 in, well, 2 by itself is an even subarray. But when you add an even subarray to an odd subarray, you get an additional odd subarray. Right? So there's an additional odd subarray if I attach myself I'm an even subarray with myself, but if I attach myself to an odd subarray, 1, 2, I get another odd subarray ending at this point. What about with 3? So now it gets a little interesting. Well, 3 by itself is an odd subarray. Now, we have information at 2, right, in this previous iteration about the odd subarrays ending at 2 and the even subarrays ending at 2. So if I'm 3, I'm my own odd subarray. I ask 2, okay, I'm odd and you have 1 odd. So if I attach myself to it, I'll become even. So I'll get 1 even subarray. And if I attach myself to your even subarray, I'll get an additional odd subarray of size 2. So I guess the basic idea here is if you have some information about this subarray ending at this system, okay? So let's say you had even and odd information about the subarrays ending at this point. And say there was 3 even subarrays at this point and 2 odd subarrays at this point, okay? And what would that look like? Well, let's say that, how are we gonna do this? Let's make this odd. Ugh, I'm all over the place today. Odd, 2. So let's say that the even subarrays up to this point are, you know, this one, these 3, and these 2. And then the odd subarrays up to this point are these 4 and these 5. So what I'm basically saying is that these 3 elements together is even. This element alone is even. These 2 elements together are even. If you add up these 4 elements, you get an odd. And if you add up these 5 elements, you get an odd. So I'm basically saying at this point, right, a subarray ending at this point, there's 3 even subarrays and there's 2 odd subarrays, right? And that even subarray is the element itself. The 3 previous elements are the 2 previous elements. The 2 odd subarrays are the 4 previous elements or the 5 previous elements. Now, if we add an additional element, let's say we add an odd number like 7, okay? Well, 7 by itself is odd. And if you take an odd and you add it to an even subarray, you'll get an odd. So 7 by itself is odd, but 7 also with these 2 additional ones are odd. So you're going to get 3 total odd subarrays, right? Now, if you take an odd and you add it to a system of odds, you get even, right? So everything that used to be odd up to this point, now that you're adding in an odd, will become even. So since this used to be, did I mess something up here? So this used to be odd, so now it becomes even. That's an even path now. And this used to be odd, and now it becomes even. So you get 2 additional even paths. So I get the 3 and then myself. So this becomes 3. This becomes 4. So let's go through that again because I think I may have messed up. Okay. So we added an odd element. Okay. We have 2 odd subarrays ending at this point and 3 even subarrays ending at this point. If we add an odd number like 7, 7 itself is odd. And if you add an odd to any even, it becomes odd. So these three even subarrays become odd. And then I add this additional 7. So now there's 4 odds. Okay. Now what's used to be odd, if you add an additional odd number like 7, so it used to be odd, you add an additional odd number like 7, it becomes even. So this path that was once odd becomes even, and this path, which was once odd, becomes even. Like so. So that increased by 1 and that decreased by 1. Interesting. Okay. Now let's think about if we add an element that is even. It should be a little bit easier. So like we add 8. Well, if you add an even to an even, it becomes even. So you have 8 itself, which is even, and then it can attach itself to this even path, and this even path, and this even path. So now you get 4 evens. And then if you add an even to an odd, it becomes odd. So there's this odd path and this odd path as well. So basically, the idea is if the element you're adding, if the num you're adding is even, the number of evens is now the previous, I guess you could call it the DP at this current num index. We'll just call it I. For even is 1 because you get the even number of adding just yourself plus the previous number of even numbers. And the number of odd numbers is, well, just whatever the previous number of odd numbers was at the previous ending subarray, because you can't attach you can attach yourself to maintain the odd, right? If you have a previous subarray which is odd and you attach an even number, it stays odd, but you don't get an additional odd subarray, so it stays the same as whatever the previous one was. Else the num is odd, right? We'll just articulate this, but it's binary. So if this isn't true, then the else clause will execute, but we'll just say else num is odd to, make it in a verbose way, articulate that we're talking about the odd case for num here. What happens here? Well, if the num is odd, then the number of even, whatever was even before, if we have an even subarray and we add an odd, it becomes odd, right? So we have an even subarray, whatever was previously odd now becomes even because you take an, wait. It's so weird with odd because it's like swapped and I'm kind of stupid. So even, whatever was previously odd, when you add in an even, the number is odd. Let's do it the other way first. Okay, so if the previous sum is the number of odd now is myself, right? Because I can add in myself because I'm odd, plus whatever was even before, because whatever was even before, if I add in an odd, it becomes odd. And that means whatever is now what's even is, well, is whatever was odd before. I probably should have articulated this more, right? Because the current number I'm looking at is odd, so whatever was previously odd will now become even, right? Versus if whatever I had was previously even and I added an odd, I get that same number of new odd subarrays plus 1 for the element itself. So this is the relationship. Now we don't need to actually keep, since we're only looking at the previous iteration, right? We could say E equals dp of I even, and O equals dp of I odd. So what I'm basically saying is we can replace all of these things with just constants, right? Because We can update even, so we could update even like this, right? So even equals 1 plus whatever even was before. Odd equals 1 plus whatever odd was before. Odd, even, odd. Right. And you notice here that odd equals odd. So this statement is kind of trivial. We don't even need this statement. This is an unimportant statement here. This last one, right? Because it's basically saying odd equals odd. Or the number of odds stays the same. So we don't need to worry about that. So let's go ahead and try to get into this solution with that stated. Okay, so we have even, odd, and we need to keep track of the total number of odds we find in each case. So we could call that total, EOT, 0, 0, 0. We'll look at each num in the array. And we'll say if the num mod 2 equals 0, so that means it's even, else it's odd. So what did we say if it was even? We said the number of even equals 1 plus the number of even before. Even plus 1. And we said odd equals odd, but that doesn't change anything, so let's just keep it like that. And then otherwise the number is odd, so what do we do then? This is where I always get confused for some reason. Odd equals 1 plus even, and even equals odd. We'll do that atomic, like on one line, so that we don't have to use like a temp variable. So even, odd. We'll say that even equals odd, and odd equals even plus 1. So that's this line here. You know, odd equals 1 plus even. Odd equals 1 plus even equals odd. Okay. And then we'll just always, at every iteration, you know, every iteration gives us information about the number of subarrays. You know, the number of subarrays that are odd ending using this as the last element in the subarray, and the number of subarrays that are even using this as the last element of the subarray. So that would mean the total equals plus equal the number of odd that you've seen. And at the end, you just return total. All right. Oh, I forgot to do what I always forget to do. All right. So what is the time complexity? Let's say n equals the length of the array. For time complexity, well, we just populate these three variables. Oh, this constant time. We have to look at each number in the array, and the array's length is n. So we have to look at all n numbers. This is a constant operation, constant operation, constant operation, constant operation. So for n numbers, we do constant operations. That's big O of n. And then for space, we create three variables, and we just update those three variables. So that's big O of 1. All right, guys, hopefully that made a little bit of sense. This is very similar to like a problem I've done recently, which is number of subarrays with even parity or something. This is essentially the same problem, but this is number of subarrays with odd sum. So you kind of have to think about what happens. If you have an odd subarray and you add an even, you get odd. If you have an even subarray, you add an odd, you get odd. If you have an odd subarray, you add an odd, you get even. If you have even, you get even. Yeah, so put that in your pipe and smoke it. All right, guys, have a good one.